we know so far that if we have a magnet or a little piece of ferromagnetic material sitting on our desk, then we know that the magnetic lines of force are going to travel in a direction from the North Pole to the South Pole. And they are going to go all the way through the material as well. These are our magnetic lines of force. We know lots of things about them. We know that they are continuous. We know that they repel each other, so they get weaker as they go further away from the magnet. They get more dense as they go into the poles. We know that there is a North Pole and a South Pole on this magnet. And we also know a bit about magnetism in terms of a conductor or a wire, which has current flowing through it. And if current is flowing through it, our right-hand rule tells us if we put our thumb in the direction of that current flow, then our fingers will show us the direction of the magnetic flux or the magnetic field lines. And these magnetic field lines will be in concentric circles, and they will be not touching each other, and they will go expand out into free space to a certain extent where they're more magnetic close to the current carrying conductor. So we know these two things, and there are very, very useful applications. If we combine these two things, we can do lots of really good work. So if we bend this current carrying conductor, we're going to take this and we're going to bend it. Imagine if I take this end and I bend those two ends together, what's going to happen to my my magnetic flux lines is my magnetic flux lines, as I start bending it, my magnetic flux lines are now in sort of this shape. They're in this shape, right? And they're closer together out in the middle here, aren't they? And they are further apart. So here's a diagram over here then. There's a diagram showing this happen. And there's my current carrying conductor. It's exactly the same as this current carrying conductor. And I have bent it. In this case, in the case that I drew over here, the current was flowing this way. Now, this one, actually, the current is flowing this way. So current is flowing the opposite way. I'm going to do my right-hand rule all over again. I'm going to put my thumb in the direction of this current going around. My fingers are saying if I do that, then the direction of the magnetic lines of flux are going to go this way. And what's happening here then is these are all pretty close together on the inside compared to the outside. So this distance is great and this distance is small. So what I've done then is I have concentrated. I have made a concentrated electric field in there. So, I mean magnetic field. It is strong. A strong magnetic field. And over here, it's pretty weak because these are all coming together. If I draw some more of these, here they are coming in, coming in, coming in, coming in. Look at these magnetic flux lines coming in. They are getting so close together. And when magnetic flux lines are close together, that's a strong magnetic force. So this is a shape called a toroid, a toroidal shape, or we can call it a donut shape because it looks like a donut. But the toroidal shape, not unlike a donut, is very, very useful because what it does is it concentrates. It concentrates those flux lines. When a current carrying conductor is straight over here, they are not concentrated. They are kind of on top of each other. As we bend that, we concentrate it and we get this situation in the middle here. This situation in the middle here is a very useful situation where we have strong magnetic field. useful for a lot of things. So that's why this toroidal shape is used quite a bit in magnetic circuits, and that's how we get to that strength um, from our right hand rule.